Hello everyone. So in this session we will be looking at what we mean by reducible polynomials, and we will prove some basic results regarding reducible polynomials. First, let us show that the units of dx are basically the units in d. By this, what do I mean? That the units in dx are only those constant polynomials which correspond to units in d. So suppose f of x is a unit in dx. This means that there exists a polynomial g of x in dx such that f of x times g of x is the constant polynomial 1, because 1 is the multiplicative identity. Now notice here that the degree of f of x plus the degree of g of x, which is the degree of f of x into g of x, is equal to the degree of 1, that is 0. So therefore, the degree of f of x is equal to 0 and the degree of g of x is also 0, which means that f of x and g of x are both constant polynomials. Let us say that f of x is the constant polynomial a and g of x is the constant polynomial b. What does this mean? This means that, as we can see here, f of x into g of x is 1. Therefore, this means that a into b would be, looking at them as polynomials, you get 1, which would mean that multiplying them in the integral domain will also give us 1, and which tells us that a is a unit in d. Okay, so what we have shown here is that f of x is the constant polynomial a and a is a unit in d, and this is what we wanted to prove. Now we define irreducible and reducible polynomials in dx. Suppose d is an integral domain and f of x is a polynomial over d which is non-zero and which is not a unit in dx, then we say that f of x is reducible if we can write f of x as some g of x times h of x, where both g of x and h of x are non-units. If f of x is a polynomial over d that is non-zero and non-unit, then we say that f of x is irreducible if it is not reducible. Remember that we define reducibility and irreducibility only over the class of polynomials which are non-zero and non-units in dx. From the previous exercise, we can observe that if f of x is a unit in fx, then it should be a non-zero constant polynomial in fx, because if f of x is a unit in fx, then we have shown that f of x should be a unit in f, which means that f of x is a constant polynomial. The converse of this statement is also true. You can try to prove it on your own. Now we will prove one important result when it comes to polynomials of degree 2 or 3. We will show that a polynomial over a field f of degree 2 or 3 is reducible if and only if it has a 0 in f. So first let us assume the direct statement. So suppose f of x is reducible. This means that there exist polynomials g of x and h of x in fx such that f of x is equal to g of x into h of x, where g and h, the polynomials g of x and h of x, are non-zero, non-unit. Now notice here that the degree of f of x is the degree of g of x plus the degree of h of x. But we know that the degree of f of x is either 2 or 3. Therefore, as the degree of g of x and h of x cannot be 0, this means that the degree of g of x and h of x is either going to be 1 or 2. Since the degree of g of x and h of x cannot be 0, it means that one of these polynomials, that is either the g of x or h of x, should be of degree 1. Let us say that the degree of g of x is 1. Okay, so since the degree of g of x is 1, we can write g of x as some ax plus b, where a and b are in the field. Therefore, we see that f of x is ax plus b times h of x, and hence f of minus b times a inverse would be a times minus b times a inverse plus b into h of minus b times a inverse, which would be 0 times h of minus b times a inverse, which is equal to 0. And therefore it tells us that minus b times a inverse is a root of f. Now conversely, let us assume that f of x has a root alpha. This means that x minus alpha divides f of x, which tells us that there exists g of x in fx such that f of x is equal to x minus alpha times g of x. Now notice here that as we are in a field and the degree of f is either 2 or 3, therefore the degree of g will be either 1 or 2, and hence g will be a non-zero non-unit polynomial. Therefore this tells us that f of x is reducible. Now we move our attention to polynomials in Zx. If an x raised to n, an minus 1, x raised to n minus 1 up to a naught is a polynomial in Zx, then we define the content of this polynomial to be the greatest common divisor of its coefficients. If the content of a polynomial in Zx is 1, we call this polynomial a primitive polynomial in Zx. Now for any n in n, we can show that this function f from the polynomials over z to the polynomials of zn given by f of x equals f bar of x, where f bar of x is attained by reducing each coefficient of f of x modulo n, is a ring homomorphism. Let us prove this statement. So let us start with two polynomials f of x and g of x. Therefore f of x plus g of x will be the polynomial obtained by adding the corresponding coefficients. Hence f of x plus g of x will be the polynomial ak plus bk bar x raised to k, that is summation k going from 0 to infinity ak bar plus bk bar times x raised to k, which is the sum of the polynomials over Zn ak bar x raised to k plus summation k going from 0 to infinity bk bar x raised to k, which is exactly f of x plus f of g of x. Now let us see what is f of x times g of x. This by definition is summation k going from 0 to infinity summation I going from 0 to k ai bk minus I x raised to k. Therefore f of x times g of x would be summation k going from 0 to infinity summation I going from 0 to k ai bk minus I bar x raised to k. Okay, and we know that this is each of these coefficients, since this is just a finite sum and finite products in the sum, we have summation I going from 0 to k ai bar into be k minus I bar. This here is the product of the two polynomials, summation k going from 0 to infinity, ak bar x raised to k, and summation k going from 0 to infinity bk bar x raised to k, which is f of x times f of g of x. Therefore, we proved that f is a homomorphism. Now, we will prove an important result in the ring Zx. We will show that given two primitive polynomials in Zx, their product is again a primitive polynomial. Suppose f of x and g of x are two primitive polynomials in Zx. We will let f of x be equal to summation n going from 0 to infinity an x raised to n, and g of x be the polynomial summation n going from 0 to infinity bn x raised to n. Here ans and bn's are all integers. Therefore, f of x into g of x will again be a polynomial in Zx. Now suppose f of x into g of x is not a primitive polynomial. This means that f of x into g of x has a content greater than 1. Now, since the content of f of x into g of x is greater than 1, we know that C has a prime divisor. Let P be some prime divisor of C. Let us consider the homomorphism as illustrated in the previous example, that is, say phi from Zx to Zpx given by phi of any polynomial h of x equals h bar of x. We have shown in the previous exercise that this is a homomorphism. Notice here that as the content of f of x into g of x is C, and since P is a divisor of C, it means that P divides every coefficient of f of x into g of x, which means that phi of f of x into g of x would be equal to 0 in Zpx. But we know that this is a homomorphism, so therefore we have phi of f of x into phi of g of x equals 0. Now, since Zp is an integral domain, Zpx is also an integral domain, which tells us that either phi of f of x is equal to 0 or phi of g of x is equal to 0. Say without loss of generality, we assume that phi of f of x is 0. What does this tell me? Phi of f of x will be 0 only if after going modulo p, each of the coefficients of f are 0. Therefore, each of the coefficients of f are multiples of p. So therefore, this means that p divides an for every n equals 0, 1 up to infinity. This tells us that p divides the content of f of x. But this is a contradiction, as f of x has content 1. Okay, so this contradicts the fact that f of x has content 1, and therefore f of x into g of x has to be a primitive polynomial. Now let us prove a simple corollary to the previous theorem. Suppose g of x and h of x are two polynomials over z that have content a and b respectively, then their product will have content ab. So we will let g of x be equal to summation n going from 0 to infinity an x raised to n, and h of x be equal to summation n going from 0 to infinity bn x raised to n. Notice here that since the content of g of x is a, this means that a divides each of the an's. Therefore, I can write g of x as a times g1 of x, where g1 of x is the polynomial obtained by dividing every coefficient by a. Notice that this is again a polynomial in Zx which has content 1. Similarly, we can write h of x as b times h1 of x, where h1 of x is summation n going from 0 to infinity bn upon b x raised to n, again which has content 1. Therefore, if we look at g of x into h of x, it will be ab times g1 of x into h1 of x. By Gauss Lemma, notice that since g1 of x and h1 of x are primitive polynomials, g1 into h1 will again be a primitive polynomial. And hence, now we are multiplying ab to the coefficients of a primitive polynomial, which means that the content of g of x into h of x will be ab. Now we will show that if f is reducible over q, then it is also reducible over z, given that f is a polynomial with coefficients from z. Suppose f is reducible over q, this means that f of x can be written as g of x times h of x, such that g of x and h of x are both in Qx and they are non-unit, non-zero. Therefore, the degrees of g of x and h of x will be greater than or equal to 1. Now notice here that g of x and h of x are polynomials over Q. Therefore, each of their coefficients can be written as an integer upon an integer. Let us say that the content of f is C. Now we take f1 of x to be 1 upon c times f of x. Now notice here that the c is the content of f. Therefore, c is the greatest common divisor of all the coefficients of f, non-zero coefficients of f. Which means that if I divide all the coefficients of f by c, the content of f1 of x will become 1, which means that f1 of x is a primitive polynomial. And we will also take g1 of x to be 1 upon c times g of x. And therefore, what you can see here is, so just by multiplying by 1 by c to the left and right of this equation, you get f1 of x will be equal to, we are not changing any degrees of polynomials here, g1 of x times h of x. This here now is a primitive polynomial. Now this is again a polynomial in Q and this is a polynomial in Q. We will let g1 of x be equal to summation n going from 0 to infinity an upon bn x raised to n, and we will take h of x to be, because this is a polynomial over Q, so we can write it this way, n going from 0 to infinity okay, where our ans, bns, cns and dns are all in z, and the GCD of an and bn is 1 and the GCD of cn and dn is 1. So we can cancel out all common factors and make it 1. There is no problem in assuming this. Let us look at A to be the least common multiple of all the bn's, that is b1, b2 up to say bk, and we'll take b to be the LCM of d1, d2 up to dm, where k is the degree of g1 of x or the degree of g of x, which is the same, the degree of g1 of x, and m is the degree of h of x. Now why do we do this? Because we only want to take some finite number. Okay, so therefore when I multiply a to g1 of x, what would happen is a times g1 of x will now be an element of zx, because this is a multiple of all the denominators in here. So all these denominators of all these bn's, a is a multiple of all bn's. Therefore, a times g1 of x will be in zx, and b times h of x will also be in zx. Therefore, we will let C1 be the content of a times g1 of x, and we will let C2 be the content of b times h of x. Therefore, what we can do here is we can write a times g1 of x as c1 times g2 of x, and b times h of x as c2 times h1 of x, where g2 of x and h1 of x are primitive polynomials. Okay, so therefore what we have is we have ab times f of x, f1 of x. Therefore we have ab times f1 of x is equal to, as you know, f1 of x is g1 of x times h of x. Therefore this will be a times g1 of x into b times g2 of x, into b times h of x. But a times g1 of x is c1 times g2 of x into b times h of x is c2 times h1 of x, which is c1 c2 g2 of x into h1 of x. Now let's look at the left hand side and the right hand side. On the left hand side, you can see that f1 of x is a primitive polynomial. Therefore the content is ab. Similarly, on the right hand side, you can see that g2 of x and h1 of x are both primitive polynomials, which means that the content on the right hand side is c1 c2. So therefore what we have is ab is equal to c1 c2. Okay, since g2 of x and h1 of x are both primitive, the product is also primitive by the Gauss Lemma, and therefore we can cancel out ab and c1 c2 to give us f1 of x as g2 of x times h1 of x. Now we want to have f of x as a product of two polynomials, so we just multiply c to it. So f of x is c times f1 of x, which is c times g2 of x into h1 of x. So here you can see, if you look through the proof, the degree of G2 is the same as the degree of G, and the degree of H1 is the same as the degree of H, which means that both of these are non-units and non-zeros because their degrees are both greater than or equal to 1. Therefore, what we have proved is that f of x, these are both polynomials in Zx. So f of x is reducible in Zx. Okay, so with this we will stop with this section. So I will see you for the next section. Thank you.